Welcome back, students. Today we're going to begin learning about the laws of thermodynamics, and we're going to start off with the first two, which are the zeroth law. It's kind of weird that you start at zero, but that's just what it's called. And then the other law we're going to talk about is the first law. The zeroth law of thermodynamics states that if two bodies or objects are in thermal equilibrium with a third one, in other words, if they are the same temperature, then those two bodies are also in equilibrium. It's easier to understand this if I provide a picture to help make sense of it, so I'm going to do that now. Okay, here I've written out the law, as I just stated. If two bodies are in thermal equilibrium with a third body, then they too are also in equilibrium. And once again, thermal equilibrium just means that they are the same temperature. And whenever things are at the same temperature, they no longer exchange heat energy. Okay, so in this example here, I have three ponds connected by streams. And if I know that ponds A and B are in thermal equilibrium, or in the same temperature, and I know pond B and C are also in thermal equilibrium, then according to the zeroth law, I know that A and C are also in thermal equilibrium, meaning they're all the same temperature. So pretty much the zeroth law just connects the dots. If we know that these two are the same temperature, and we know these two are the same temperature, then these two also have to be the same temperature. The next law of thermodynamics that I'm going to talk about is the first law of thermodynamics, which is pretty much just an adapted form of the conservation of energy. So in the energy unit, we learned that energy is conserved, which means that it cannot be created or destroyed, only transformed between different types of energy. The first law of thermodynamics pretty much states that energy is conserved, but it applies it to thermodynamic processes. The first law of thermodynamics says that the internal energy of something is equal to the heat energy minus the amount of thermodynamic work being done by the system. And I can put this in equation form. Okay, so once again, the first law is just the conservation of energy, but applied to thermodynamic processes, where the total change in internal energy is equal to the heat added minus the work done by the system. Okay, we use a U to notate the internal energy, we use a Q to notate heat energy, and we use W to notate work. If I use myself as an example, and I'm trying to apply this equation to me, and I'm trying to track my change in internal energy, if heat is added to my body, or if I go out in the sun, then the Q is going to be positive. I'm going to increase my energy. But if I go into a freezer, then I'm losing heat energy, then Q is going to be negative. If work is done by me, or if work is done by the system, then work is going to be positive, because if I'm doing work, then I'm losing energy. So if this is positive, then it's going to get subtracted from my internal energy. And if work is done to me by something else, then I'm receiving that energy, so this would be negative. So then the negatives would cancel, and it would be positive. Okay, I drew a simple picture here to help you understand how to use this equation. Let's say I want to know what change of internal energy is happening with this character here. He's doing some work himself on this box. Let's say he pushes with a force of 5 newtons over a distance of 1 meter. Work is equal to force times distance, so that'd be 5 joules. So he's doing 5 joules of work, and he's also getting beat down by the sun, which transfers another 5 joules of heat energy into him. Okay, then my total internal change of energy would be just 5 minus 5, which comes out to 0. They cancel out, because as he's losing energy from doing work on the box, he's receiving energy from the sun. If instead of him pushing a box, someone else was pushing him, then work would be done on the system, and I would have to make this negative. Like, if instead of him pushing a box, there was someone else pushing him from behind, and that other person pushes him with overall work of 5 joules, then work is being done on him, not by him. So this would be negative 5, and then minus a negative 5 would be plus. So then the total energy of that person would increase by 10 joules. But either way, energy is conserved in both those examples, and we use this equation to understand where the energy comes from and where it's going. Okay, I hope this video helps you guys make sense of the first laws of thermodynamics, the zeroth law and the first law. Tomorrow we'll talk about the second and the third law. Okay, see you guys next time.